Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video is part 3 on derivatives and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended that students view derivatives part 1 and 2 prior to watching this video. In this video, we will be discussing implicit differentiation, exponent functions, log and natural log functions, related rates, and minima, maxima, and critical points. Functions of the form y equals f of x can be differentiated because y is expressed explicitly. There are equations, however, that do not fall under this rule. For example, the equation of the unit circle x squared plus y squared equals 1 cannot be solved for a single y, so it is not even a function. However, it can be differentiated. First, we take the derivative of both sides of the equation and for each term. The first term is easy. The derivative of x squared is 2x. If we consider the second term y as a function of x, or y equals f of x, then y squared is equal to f of x squared. To take this derivative, we use the chain rule. d dx of y squared equals 2 times f of x times the derivative of f of x, which is dy dx. This gives us d dx of y squared is equal to 2y dy dx. On the other side of the equation, the derivative of a constant is 0. Next, we solve for dy dx by first subtracting 2x from both sides, then dividing by 2y. When we simplify, we get dy dx is equal to negative x over y. With y in the denominator, this holds only for y not equal to 0. If we look at the graph of the unit circle, we can see that this is consistent. When y equals 0, the tangent line is vertical, and as such the slope is undefined. As an example, let's use implicit differentiation to find dy dx in the equation y is equal to x e to the y. First, we take the derivative with respect to x of both sides. On the right side of the equation, we use the product rule and take the derivative of x times e to the y plus x times the derivative of e to the y. The derivative of x is 1, leaving e to the y in the first term. Next, we use implicit differentiation to find the derivative of e to the y. As in the last example, we express y as a function of x, then use the chain rule. The derivative of e to the f of x is e to the f of x times the derivative of f of x, which is dy dx. So the derivative of e to the y is e to the y dy dx, and that times x is the second term. Next, we move the terms containing dy dx to one side of the equation and factor it out, leaving dy dx times the quantity of 1 minus x e to the y equals e to the y. Next, divide out all but dy dx to get dy dx is equal to e to the y over 1 minus x e to the y. Next, let's look at the exponent functions. Let f of x equal a to the x for all a greater than 0 and a not equal to 1. And let's find the derivative. Since we have already solved the derivative of e to the x, let's start by expressing a to the x as equal to e to the x natural log of a. Next, we take the derivative with respect to x. Using the chain rule, we take the derivative of e to the x natural log of a times the derivative of x natural log a. Natural log a is a constant, so the derivative of a to the x is a to the x natural log of a. As an example, let's take the derivative of y equals x to the third times 3 to the x. Using the product rule, dy dx is equal to 3x squared times 3 to the x plus x to the third, 3 to the x natural log of 3. We can simplify to x squared 3 to the x times the quantity of 3 plus x natural log of 3. In earlier lessons, we covered the idea of the natural exponent function f of x is equal to e to the x. Since this is a one-to-one function on the interval of negative infinity to infinity, then it has an inverse function f inverse of x is equal to the natural log of x. Let's look at the natural log function. Y is equal to natural log of x, which can also be stated as x equals e to the y. Next, we differentiate both sides with respect to x. ddx of x is 1, ddx of e to the y is e to the y dy dx. Divide e to the y from both sides and replace e to the y with x. Therefore, ddx of the natural log of x is 1 over x. As an example, find the derivative of the following function. Y is equal to the natural log of x squared. For this function, we use the chain rule. Let u equal x squared, which would make y equal to the natural log of u. Du dx will be 2x, and dy du would be 1 over u. dy du times du dx equals 1 over u times 2x, or 2x over u. So dy dx equals 2x over x squared, which simplifies to 2 over x. Next, we examine the function f of x is equal to log base b of x, where b in the function must be greater than 0 and not equal to 1, and we try to find the derivative. We first start with the change of base formula, log base b of x equals natural log of x over natural log of b. Since the natural log of b is a constant, we can pull it out. So ddx of the natural log of x over the natural log of b equals 1 over b ddx natural log of x. ddx of the natural log of x equals 1 over x, so the derivative of log base b of x is 1 over x times the natural log of b. As an example, let's find the derivative of y equals 4 times log base 3 of the quantity of x squared minus 1. Again, we use the chain rule. Let u equal x squared minus 1, so y equals 4 times log base 3 of u. Du dx equals 2x, and dy du equals 4 over u times the natural log of 3. dy du times du dx equals 4 over u times the natural log of 3 times 2x, or 8x over u natural log of 3. Replace u, so dy dx equals 8x over the quantity of x squared minus 1 times the natural log of 3. In a related rate problem, we are given two variables that change with respect to time. These variables will be related by an equation or relationship. If we are given the rate at which one changes, we can determine the rate at which the related variable also changes. For example, let's say liquid is flowing out of the bottom of a conically shaped container at a rate of 2.25 cubic inches per minute. If the dimensions of the cone are 2 inches in radius at the top and 5 inches in height, at what rate does the height of the liquid decrease when the height is 3 inches? With these problems, it is often helpful to have a diagram. We can start by knowing the volume of the cone is equal to 1/3 pi times the radius squared times the height. Since we are relating the height to the volume, we need to speak of our equation only as it relates to the height. Since the ratio of the radius to the height is 2 to 5, we can replace in our volume equation r with 2 over 5 times h. Now our volume equals 4 over 75 times pi times the height cubed. Now we take the derivative of the volume with respect to time and use implicit differentiation for the height with respect to time. dy dt will be on the left side, and the derivative of the height with respect to time on the right side will be 4 over 25 times pi times the height squared. We are given a volume with respect to time is 2.25 cubic inches per minute, and the height at 3 inches. So replace dv dt with 2.25 and the height with 3 inches. Now we solve for dh dt and complete the arithmetic to arrive at 0.497 inches per minute. Let f be defined on a domain containing C. If f of c is greater than or equal to f of x for every x in the domain, then f of c is an absolute maximum. If f of c is less than or equal to f of x for every x in the domain, then f of c is an absolute minimum. The maximum or minimum may occur at the edge of the domain or at some midpoint as depicted in the two graphs. The following theorem applies. A function is continuous on a closed interval, has an absolute maximum and an absolute minimum. Suppose C is an interior point of some interval L on which f is defined. If f of c is greater than or equal to f of x for all x in L, then f of c is a local maximum. If f of c is less than or equal to f of x for all x in L, then f of c is called a local minimum. The concept of local minimum and maximum is easier to comprehend when looking at a function's graph. Note the local minimum and maximum are not the absolute minimum and maximum. The theorem states that if f has a local maximum or minimum value at c, then f prime of c exists and f prime of c equals 0. We can then define an interior point C of the domain of f at which f prime of c equals 0, or f prime of c fails to exist, is called a critical point. Suppose a second derivative of f exists on an open interval L. If that second derivative is greater than 0, then f is concave up on L. If that second derivative is less than 0, then f is concave down on L. If f has an inflection point at c, then the second derivative of f at c equals 0. Now let's combine what we know to find and evaluate the critical points in the function f of x is equal to x to the fourth minus 4x cubed plus 4x squared on the closed interval -1 to 3. First, we can find f prime equals 4x cubed minus 12x squared plus 8x. Also, the second derivative equals 12x squared minus 24x plus 8. Next, we find where the first derivative equals 0. If we set 4x cubed minus 12x squared plus 8x equal to 0, we can factor getting 4x times the quantity of x minus 2 times the quantity of x minus 1. This means the critical points exist at x equals 0, 1, and 2. If we solve f for each of these points, and for the boundaries of the domain and graph, f of -1 equals 9, f of 0 equals 0, f of 1 equals 1, f of 2 equals 0, and f of 3 equals 9. Next, we look at the second derivative at the three critical points. The second derivative of f at 0 is 8, meaning concave up. The second derivative of f at 1 is -4, meaning concave down. And the second derivative of f at 2 is 8, meaning concave up. Knowing this, we can conclude that the two endpoints are absolute maximums. The point 1, 1 is a local maximum, the point 0, 0 is an absolute minimum, and the point 2, 0 is also an absolute minimum. With this, we can now draw our graph with a fair degree of accuracy. If we look at where the second derivative equals 0, we will get the boundaries of the concavity. Solving 12x squared minus 24x plus 8 for 0, we get x equals 3 plus or minus the square root of 3 over 3, or 0.42 and 1.58. Therefore, f is concave up on the interval -1, 0.42, and 1.583, and f is concave down on the interval 0.42, 1.58. If you have further questions on this or any other math topic or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you and good luck with your studies.